work based on surface area. Yeah. Our whole focus really, and Richard's focus when he invented this system, was to create a device that would be low in maintenance. Because in the United States, everybody's tired. The utility companies are tired of fixing these big systems. Too much big cranes, too much downtime. And so economically it affects the performance of the units.
Right.
So we wanted to get back to something that's smaller. We're not very big, okay? Standard 65 feet tall. Two men in 2 hours can fix any component on the system. We eliminated the transmission. We do not feather props. There's no feathering of the props.
Right.
The mechanical steerage is gone because it steers like a parachute. When the parachute receives wind, it will automatically just reposition itself around a standard. So we don't have mechanical servo mechanisms here. We don't feather props, all that's eliminated. We don't have a transmission in there. When General Electric hangs these big ones, they hang 55 tons in the air for the total apparatus. 7 tons of that is a transmission. It's gone, no more. So we don't have to maintenance and service that.
Right.
And that's very important because what we were after was the ability for these things in remote areas to work without a lot of personnel having to bring major crane systems in to repair them. And by eliminating that, it adds money to the profitability, you know. The reality of it is the capital cost is only one aspect of the money. The real money in the industry that's being spent today is when you get this installed and it only works 5 hours a day or 3 hours a day. And by creating the device that allows us to capture energy from 5 miles an hour all the way up to 90 miles an hour in wind speed, elongates the ability to create energy over a 24-hour period. So your kilowatt hour output is much higher in a device that is not so sensitive to wind speeds. And so normal generators make energy from about 12 miles an hour to 28 miles an hour. Then they start to shut them down. And when the wind's blowing the best, they cut them off. Because the airfoil designs cannot handle that much wind. This device, when it loads up energy, okay, at 5 miles an hour, maybe only a few of these coils are working. When it gets to 20 miles an hour, there might be 30 or 40 coils working. When it gets to 30, 40 miles an hour, 300, 400 coils are working. It's got a load sensor in here that senses the velocity and the torque, and as the torque goes up and the velocity goes up, it puts more of these cells on. More of these kick in. And consequently, the thing about the wind is it's never constant. So it could blow up to 70 miles an hour and then all of a sudden slow back down to 10 miles an hour. There's enough inertia in these discs right here that it acts like a flywheel. The inertia is already built up, so if the wind's blowing at 30 miles an hour and all of a sudden goes down to 10, the load sensor, the electronics sense the difference in load and lays off the coils. If the wind picks back up, it lays on the coils. Now the beauty of that is over 30 miles an hour, 40 miles an hour, 50 miles an hour, we don't have a mechanical brake on this. And a mechanical brake grabs this and it creates heat to slow it down, to stop it, okay? We don't do that. When we get up into the higher wind zones, Richard makes more power, okay? Because what we're after is we want the load to act as the brake. So we add more load, we add more of these. 50 miles an hour, maybe 200 coils are employed, 300 coils. That creates load and puts out more energy to the grid in high winds. And then it also acts as resistance that slows down the blades in high wind. So we're not wasting the wind energy in high velocity winds.
So it becomes a government. Yeah.
Exactly.
Right.
Yeah. So this design is the first breakthrough in electrical generation like this since 1870 in generators. It's very important because our whole goal here is to eliminate downtime and have standard utility trucks with pole cranes and two-man standard lifts to go out and fix these things when they break. Because if you can do that, then you eliminate 2 or 3 months of downtime to bring big trains in, mobilize the cranes. An average service call costs between $250,000 and $500,000. Utility companies can't afford that. Countries can't afford that. This is the first technology that you see that can create sustainable energy under coal-fired power in good wind in terms of operating